Welcome to techaily.ai, your shortcut to being well informed on the most compelling tech topics. Today, we're taking a deep dive into, well, the true muscle of your computer, the graphics card. We're not just going to define terms, we really want to explore why this component is just so incredibly impactful. And before we pull back the curtain, just a quick shout out to our fantastic sponsor, Stonefly. Whether your needs are enterprise storage, robust backup disaster recovery, cutting-edge hyper-converged VMware, Hyper-V, Proxmox cluster solutions, or even powerful AI servers, Stonefly is really your trusted solution provider and advisor. They also offer SA365, that's a turnkey security appliance, and just unparalleled expertise in both public and private cloud environments. You can find out more over at stonefly.com.
Yeah, and our mission today is really to get under the hood of these graphics cards. We'll go beyond just the basics, dissecting their core components and, the really intricate processes that bring those amazing digital images to life right there on your screen. And understanding this isn't just for gamers, actually. It's pretty crucial for anyone navigating today's tech landscape.
Yeah.
We're here to make that complex information accessible and, well, hopefully captivating for you.
Okay, let's dive right in then. Most of our listeners probably know a GPU is essential for gaming and, creative work. But what's maybe often misunderstood about its core function, especially when you compare it to the CPU? What's its unique job?
Well, that's a great starting point. While some CPUs do have integrated graphics, which, share system resources with the main processor, a dedicated graphics card is a completely separate powerhouse. It's like having this specialized, hyper-efficient visual processing unit. It's got its own brain, the GPU itself, its own really fast short-term memory, which we call VRAM, and its own dedicated power and cooling systems.
Right.
This independence is precisely why it's indispensable for demanding stuff, like mid to high-end gaming, complex 3D animation, intensive video editing. It completely offloads all that visually heavy work from your CPU and your system RAM. And that leads to a massive overall performance improvement across your entire computer, really.
Oh, okay. So it's not just more powerful, it's fundamentally designed for a different kind of processing. That clarifies a lot. And it's certainly not a one-size-fits-all component, is it? There's just a huge spectrum of cards out there.
Absolutely. A huge range. You'll find options for pretty much every budget and need. From, excellent entry-level cards that handle everyday tasks and maybe some lighter gaming, all the way up to high-end beasts and even specialized professional cards you'd find in data centers. Plus, they come in various physical sizes. There are even low-profile options, which are perfect if you're building, say, a compact system or maybe a home theater PC.
Right. Given that dedicated design, let's sort of peel back the layers now and explore the intricate components that make all that visual magic actually happen.
Yeah.
What are the key pieces inside that powerful unit?
Okay, so when you look inside a graphics card, despite the different shapes and sizes, they all share the same core components. First up, obviously, is the graphics processing unit, or GPU itself. This is the real brain of the operation. Inside, you've got millions, sometimes billions, of tiny switches called transistors, along with specialized components like NVIDIA's SUDI cores or AMD's streaming multiprocessors. They all work simultaneously in parallel to accelerate 3D image rendering. It's basically a parallel processing monster, handling thousands of calculations at once, just what graphics need. Next, you have video memory, or VRAM. Now, this isn't just storage. It's more like a dedicated high-speed workspace just for the GPU. It's physically located much closer to the GPU chip than your standard system RAM, which means incredibly fast data transfer and minimal lag. VRAM stores all the critical information the GPU needs right away, things like high-resolution textures, that's the image data giving surfaces detail, and shaders, which are like mini programs telling the GPU how to color and light things. Then there's the voltage regulator module, or VRM. This is absolutely vital. It ensures the GPU gets a constant, steady supply of power, which is crucial because graphics cards can have, widely fluctuating power needs. High-end cards, for example, often need external power connectors directly from your power supply. We're talking those 6-pin, 8-pin connectors, or even the newer, really beefy 16-pin 12VH PWR connectors. Those could deliver a staggering 600 watts just from a single cable on cards like the RTX 4090 or 4080.
Wow, 600 watts just for the card. That's serious power.
It is. Then you've got the PCIe interface. Think of this as the high-speed highway connecting the graphics card to your motherboard. Usually it's a PCIe by 8 or by 16 slot. Even the fastest GPU is useless if its data can't travel quickly back and forth to the CPU, right?
Makes sense. A bottleneck.
Exactly. And speaking of keeping things running smoothly, the cooling system is absolutely paramount. All graphics cards have integrated heat sinks and fans. They're designed to efficiently pull heat away from those hard-working components to maintain optimal performance. On the really powerful cards, you'll see these massive air coolers or sometimes even self-contained water cooling loops. You'll also often find an interconnection interface, things like NVIDIA NVLink or AMD Crossfire X. These let you link multiple graphics cards together. Now, this is becoming less common for consumer gaming, honestly. Modern single GPUs are just so powerful that the gains from linking cards often aren't worth the cost or complexity anymore for gamers. But it's still widely used in high-performance workstations and supercomputers, where you just need absolute raw compute power. The Video BIOS, or vBIOS, is like the card's basic firmware, a minimal program for its initial setup and control. It lets you make adjustments to settings like clock frequencies or fan speeds, usually through specialized software provided by the manufacturer. And finally, the output interfaces. These are simply the physical ports you use to connect your monitor. You'll typically see DisplayPort, DVI, HDMI, and sometimes even USB-C on newer cards. Oh, and yeah, for those who love customization, there's often RGB lighting too, usually controlled via your motherboard's software.
Because what's a powerful rig without some colorful glow, right?
Pretty much.
So it really is like a tiny, complex computer all on its own, just living inside your bigger computer, dedicated purely to visuals. It's quite ingenious how all those pieces work together. But okay, that's the hardware. How does it actually translate abstract data, code and numbers, into the stunning visuals we see on screen? That's where the rendering pipeline comes in, I gather, which sounds like a really fascinating process.
It really is. The graphics rendering pipeline is essentially a step-by-step process. It transforms a 3D scene described by data into the 2D image you ultimately see on your monitor. And it actually starts before the GPU gets heavily involved on your computer's main processor, the CPU. This is called the application stage. This is where scene changes happen, things triggered by user interaction, maybe character animation starting, new objects appearing in the world. Once the CPU processes those changes, the scene data, usually broken down into basic shapes called primitives like triangles, lines, and points, is passed over to the GPU.
Okay, so the CPU sets the stage, then hands it off.
Exactly. Then we move into the geometry stage, which happens on the GPU. This stage deals with the actual shapes and forms of objects in 3D space. Objects are defined by vertices. These are just points in 3D space. These vertices are then grouped together to form polygons, and the most common polygon used in graphics is the triangle. Simple, efficient. Each tiny triangle is defined by its corners, its vertices, and it also has something called a normal vector, basically an invisible marker telling the GPU which way the triangle surface is facing. That's crucial for figuring out how light should bounce off it correctly.
So the direction matters for lighting.
Absolutely. These objects exist within various coordinate systems. You have the object's own local system, then the world system where all objects live together, and the camera system, which represents the viewer's perspective. Objects get transformed within these systems. They can be moved, translated, rotated, or scaled. Next comes projection. This is where the 3D view gets mathematically transformed for the flat 2D screen. This could be a realistic perspective view, where things get smaller further away, or a flat orthogonal view, like in some strategy games or diagrams. This stage also handles clipping, basically, discarding any parts of objects that fall outside the viewer's field of vision. No point rendering what you can't see, right?
Saves processing power. Makes sense.
Definitely. Lighting is applied here, too. The GPU calculates how various light sources in the scene hit each surface, making objects look realistic based on their material properties. Is it shiny metal, rough stone, or maybe something else? And finally, the window viewport transformation maps that calculated image to the specific rectangular area of your screen where it will actually be displayed. After all that geometry work, we hit rasterization. This is a really critical step. It's where those continuous geometric primitives, the triangles, get converted into discrete fragments. You can think of fragments as potential pixels. This is also where Z-buffering comes into play. It's a technique used to figure out which surfaces are visible when objects overlap. Essentially, the fragment closest to the viewer gets drawn, making sure foreground objects correctly hide things behind them. Depth perception, basically. These fragments are then colored based on interpolating the properties from the triangle's vertices, the lighting calculations, and applying textures. And one more thing to ensure a smooth experience: double buffering. To stop you from actually seeing the image being drawn pixel by pixel, which would look flickery and awful. The rendering happens in a hidden memory area called the back buffer. Once the complete image is ready there, it's instantly swapped with the image currently on screen, the front buffer. This swap happens very quickly, making the whole process appear seamless to your eyes.
That's fascinating how it all breaks down into these distinct stages. It's like an assembly line for pixels. You mentioned shaders earlier when talking about VRAM. How did they revolutionize this pipeline? What was it like before shaders, and what did they enable that wasn't possible?
Oh, shaders completely transform graphics. Before shaders became common, GPUs used what were called fixed-function pipelines. This meant the hardware was designed to perform only a specific predefined sequence of operations for rendering. If you were a game developer and wanted a specific visual look, you were pretty much constrained by what the hardware was hardwired to do. There wasn't much flexibility.
So less creative control.
Much less, yeah. Shaders changed all that. They're essentially small programs that developers can write, which run directly on the GPU. This gives them immense flexibility and customization for visual effects. There are different types. Vertex shaders operate on the properties of each individual vertex sink, transforming its position in 3D space, calculating its color, figuring out texture coordinates. Then you have pixel shaders, often called fragment shaders. These run for each fragment generated during rasterization and compute its final color and other attributes determining what you actually see on the screen for that pixel. And more recently, we have things like geometry shaders and tessellation shaders. These are even more advanced. Geometry shaders can actually create new primitives on the fly, while tessellation shaders can dynamically subdivide meshes, adding more triangles to make surfaces smoother or more detailed right when needed. Shaders are the reason modern games look so incredibly diverse and detailed. Hyper-realistic lighting, complex water effects, weird distortions, post-processing filters like film grain, that's all achieved through these powerful programmable mini-programs. They replace that rigid, fixed pipeline with incredible flexibility.
Right, that programmability seems key. Now, let's dive into something that really sets modern GPUs apart and, well, has been generating a lot of buzz in recent years. Ray tracing. What exactly is it, and why is it considered such a game changer for visual fidelity?
Ray tracing, yeah, it's a really sophisticated rendering technique. The goal is to model how light actually behaves in the real world to generate digital images with incredible photorealism. It's fundamentally different from traditional rendering methods, like the rasterization pipeline we just discussed, which often use clever approximations and tricks to simulate lighting effects. Ray tracing instead literally traces the path of imaginary rays of light. But interestingly, it usually works backwards from the viewer's eye or the camera. A ray is cast out through each pixel on the screen into the 3D scene.
Backwards from the eye, that sounds counterintuitive.
It does a bit, but it's much more efficient computationally than trying to simulate every single light ray bouncing off a light source, most of which would never even reach the viewer. So when one of these rays cast from the eye hits an object in the scene, the algorithm calculates the color of that object at that point. But crucially, it doesn't necessarily stop there. That ray can then bounce. It might reflect off a shiny surface like a mirror. It might refract, bending as it passes through a transparent object like glass or water. Or it might cast what's called a shadow ray towards the light sources in the scene to see if that point is in shadow. Each bounce simulates how light behaves in reality, gathering more information about the scene's overall lighting and how surfaces interact.
So it's mimicking real physics much more closely.
Exactly. And because of this physical simulation, effects like realistic reflections, seeing the environment accurately reflected in a metallic surface, proper refractions, how objects look distorted through glass, and incredibly lifelike soft shadows. These become natural outcomes of the process, things that are often quite difficult or faked using traditional rasterization techniques. It can also naturally produce effects like depth of field, where objects blur based on distance, and motion blur.
Okay, but what's the catch? It sounds computationally intensive.
And historically, it absolutely was. Hugely intensive. For decades, ray tracing was primarily used in offline rendering for things like movie CGI, where you could afford hours per frame. It was just far too demanding for real-time applications like video games, where you need 30, 60, or even more frames per second. However, a major breakthrough came when modern GPUs, starting significantly with NVIDIA's RTX series and now also AMD's RDNA cards, began including specialized hardware acceleration. These are often called ray tracing cores or similar. They are dedicated parts of the GPU specifically designed to speed up the calculations involved in ray tracing, particularly the ray intersection tests. This hardware acceleration has made real-time ray tracing feasible in games.
Ah, so the hardware caught up.
It did. But even with acceleration, enabling ray tracing still significantly impacts frame rates. It's still a very demanding process. That's why you often see it paired with intelligent upscaling technologies like NVIDIA's DLSS or AMD's FSR. These use AI or sophisticated algorithms to render the game at a lower internal resolution and then smartly upscale it to your target resolution, like 1440p or 4K. This helps claw back some of the performance lost by enabling ray tracing, giving you a good balance of visual fidelity and smooth gameplay.
Right, the upscaling tech is crucial for making it practical. So what does this all mean for you, the user, playing a game or using an application?
Well, fundamentally, it means the potential for more immersive, visually stunning experiences. Games that utilize ray tracing well can look significantly more realistic. Environments feel more grounded, lighting behaves more naturally, reflections add depth. It pushes the boundaries of digital realism closer to what we see in the real world. Of course, developers have to actually implement ray tracing in their games, and it can usually be toggled on or off in the settings, allowing you to choose between maximum fidelity or maximum performance based on your preference and your hardware's capabilities.
Okay, that makes sense. We touched on VRAM earlier talking about components, but let's really clarify why this dedicated memory is so critical. I think we've all seen that annoying texture pop in games sometimes where textures suddenly appear or switch from blurry to sharp. That's often a classic symptom of VRAM struggling, right?
Absolutely, that's a perfect example. VRAM isn't just, a storage locker for graphic stuff. It's the GPU's immediate lightning-fast workspace. It's scratch pad, if you will. It's where the GPU stores all the graphical data it needs to access right now to render the current scene. This includes everything from those high-resolution textures you mentioned to the frame buffers which hold the image currently being constructed, the Z buffers that manage depth information, vertex buffers containing geometry data, and even the compiled shader programs themselves. It's all about providing the GPU with incredibly quick, low-latency access to the massive amounts of data it chews through every second.
So speed and proximity are key.
Exactly. And the amount of VRAM capacity you have directly affects graphics performance, especially at higher resolutions and settings. If your graphics card doesn't have enough VRAM for the assets the game wants to load, like large, detailed textures for a 4K display, it has to constantly shuffle data back and forth between the fast VRAM and your much slower system RAM via the PCIe bus. This constant swapping is inefficient and leads to noticeable performance problems. You get reduced frame rates, stuttering or hitching, and yes, that frustrating texture pop-in where blurry low-res textures are displayed until the high-res ones can finally be loaded into VRAM. In really extreme cases, if a game or application demands more VRAM than your card has, it can even lead to crashes.
Okay, so how much do you actually need? It seems like the recommendations keep going up.
They do, yeah. The amount of VRAM needed really depends on a few key factors. First, the resolution you're playing at. Higher resolutions like 1440p or especially 4K require significantly more VRAM than 1080p because the textures and frame buffers are just bigger. Second, the graphical settings you choose within the game. Turning up texture quality to ultra obviously demands more VRAM. Things like ray tracing can also increase VRAM usage. And third, just the overall complexity of the game or application itself. Some modern titles are incredibly asset heavy. As a general recommendation these days for 1080p gaming, maybe 6GB is okay, but 8GB is safer. For 1440p, 8GB is often the minimum, 1012GB is better, and for 4K you really want 12GB, 16GB, or even more on the highest end cards, especially if you want to max things out.
And what types of VRAM are we talking about? Is it just like the regular DDR RAM in my computer?
Not exactly, no. While it is a type of dynamic random access memory, VRAM uses parallelized types designed specifically for the high bandwidth, low latency needs of graphics processing. You'll commonly see GDDR graphics double data rate memory. We've gone through generations like GDDR5, GDDR6, and now even GDDR6X, which offers even higher speeds. On some very high-end professional cards, and sometimes top-tier consumer cards, you might also see HBM, or high bandwidth memory. This uses a different approach with stacked memory chips connected over a very wide interface for massive bandwidth, but it's generally more expensive. Besides the type and capacity, the memory bus width and clock speed are also crucial factors for VRAM performance. A wider memory bus measured in bits like 128-bit, 256-bit, or 384-bit allows more data to be transferred between the GPU and VRAM simultaneously. Think of it like having more lanes on the highway. Higher clock speed means the data moves faster down those lanes. Both contribute directly to overall graphics performance.
Okay, and just to be clear for listeners, you can't usually upgrade the VRAM on your graphics card later, can you?
That's a really important point. No, on consumer graphics cards, the VRAM chips are soldered directly onto the card's circuit board. They're not like system RAM sticks that you can easily swap out. So if you find you need more VRAM down the line, it almost always means you need to buy a completely new graphics card with a higher VRAM capacity. That's why choosing a card with enough VRAM for your expected usage and resolution from the outset is pretty critical.
Right. So understanding VRAM really helps you make those informed decisions when choosing a card, balancing that capacity with the overall processing power of the GPU itself. That's a crucial takeaway for anyone looking to build or upgrade their system. But, beyond just making games look amazing, GPUs are doing so much more these days, aren't they? What other surprising areas are they transforming?
Oh, definitely. While gaming is undoubtedly a huge driver for GPU innovation and sales, these incredibly powerful processors are increasingly being used for what's called general-purpose computing, often abbreviated as GPGPU. This basically means using the GPU's massively parallel architecture to accelerate tasks far beyond just rendering graphics. It allows them to take on computationally intensive workloads that might otherwise bog down the CPU, or tasks that benefit hugely from parallel processing.
Like what kind of tasks?
Well, a massive one right now is AI and machine learning. Training complex AI models involves performing vast numbers of matrix calculations, something GPUs are exceptionally good at thanks to their parallel design. So there's a forefront of AI research and deployment. We're also seeing them heavily used in scientific computing and big data processing, running complex simulations, analyzing huge data sets, things like molecular dynamics, weather modeling. And for a while there, they were famously used extensively in cryptocurrency mining. Remember when it was almost impossible to buy a high-end graphics card?
Oh, yeah, the great GPU shortage.
Exactly. That was largely driven by demand from crypto miners because the algorithms used for mining certain cryptocurrencies were highly parallelizable and ran very efficiently on GPUs. That specific demand has cooled off quite a bit now, but it really highlighted the raw compute power and versatility these cards possess. It also shows how the market has kind of shifted. While overall GPU shipments might fluctuate, there's a huge focus now on the high-end segment, not just for elite gaming, but for these demanding professional and scientific computing tasks. And that market is largely, almost entirely, dominated by the duopoly of AMD and NVIDIA. They're the two main players designing these powerful chips.
It's incredible how this component, originally designed just for visuals, has evolved. It truly shows that graphics cards are not just for entertainment anymore. They really are becoming foundational technology for the future of computing, driving innovation across so many different industries.
Absolutely. It's been a remarkable transformation. And, as we wrap up this deep dive, it maybe leaves you with a provocative thought to consider. As GPUs become even more powerful and even more central to everything from rendering unbelievably complex virtual worlds and simulations to processing the massive data sets needed for advanced artificial intelligence, how will their ongoing evolution continue to reshape not just our entertainment, but entire industries? How will they keep driving innovation in ways we can probably barely even imagine today?
That is a powerful thought indeed. Where does this core technology take us next? Fascinating stuff. And speaking of powerful solutions, this deep dive today was made possible by Stonefly. Make sure you check out their incredible offer, a 100 TB immutable and air-gapped SSO NAS, that's network-attached storage, for just $8,995. You can find out much more about that and all their other solutions at stonefly.com. Thanks for joining us on techaily.ai.